In this video, we'll be talking about observational study designs and measures of excess risk. This material appears in chapters 11 and 12 of the textbook. Our learning objectives are to identify the distinguishing characteristics of cohort and case control studies, talk about the measures of association that we use in these two studies, the relative risk in cohort studies and the odds ratio in case control studies. We'll talk about the strengths and weaknesses of both study designs, and then distinguish between absolute and relative measures of risk and interpret measures of absolute and relative risk. So we've seen this before, but epidemiology is the study of the distribution and determinants of health-related states or events and the application of that knowledge to control health problems in populations. So we talked before about descriptive epidemiology, which focuses on studying the distribution of disease. And now we're really focused on identifying the determinants or risk factors for those diseases. We also have talked about using incidence, prevalence counts, and rates to describe the burden of disease in populations as part of descriptive epidemiology. And so now we'll move on to exploring those risk factors. A little bit more terminology before we jump in. First is exposure and outcome. So usually we are talking about whether an exposure or a risk factor causes an outcome, which could be a disease, a health event, or some other health-related state of interest. A mediator is a variable through which the exposure causes the outcome. And a confounder, as we've discussed before, is a variable that obscures that relationship that we're interested in. So it's something that influences both the exposure and outcome and could result in bias in our estimates if we don't account for it. So here's a graphical depiction that we'll come back to later that shows our primary exposure of interest is having a caregiver, and the outcome is self-management behaviors for chronic disease. And then there are all these other factors that might relate to this relationship that we're interested in. And some of those, primarily those in the top left of the screen, are confounders. So things like age, other health conditions, health status, and activity limitations. So taking the last one as an example, if someone has an activity limitation, they may be more likely to have a caregiver for that reason, and it also might make it more difficult for them to engage in self-management behaviors. So if we don't measure and account for activity limitations in people in our study, we might come up with false results for the association between having a caregiver and self-management. On the bottom, you see a label for mediators there. So social support and self-advocacy are potential mediators of this relationship. So in other words, by having a caregiver, that probably increases someone's social support, which in turn increases their ability to engage in self-management behaviors. So if we were doing this analysis, we wouldn't necessarily want to adjust for social support because it's a mechanism by which we think that the exposure is related to the outcome. So now let's talk about study designs that we use to explore risk factors and determinants of disease. So observational studies are those in which we just watch what's going on. So these are not randomized trials. We're not intervening to identify or assign people to an exposure group or an unexposed group or to test an intervention. We're just seeing what people naturally do, what behaviors they engage in, what exposures they have, measure those, and determine what the association with the outcome we're interested in is. We use these pretty frequently in public health, largely because of ethical considerations. So there are lots of risk factors we want to explore that we have reason to believe would be associated with negative health outcomes. So it wouldn't be ethical to randomize people to, for example, smoking or to living in poor quality housing. So instead, we just use observational data and see what happens to people who choose to engage in those behaviors or who live in certain conditions. So what is a cohort? A cohort is just a group of people that's followed over time, and these people share some kind of common exposure or experience within a specific setting. So one example would be all of the students who entered the MHA program at App State in the same semester. That's one cohort of students. In terms of epidemiologic studies, there are lots of different characteristics that we could use to define a cohort. Some common ones are birth year or age, place of residence or geographic area. The Framingham study is a large study that started in the 50s and is an example of that. The goal was to investigate the causes of cardiovascular disease, but everyone in the study was selected from this town, Framingham, Massachusetts. Cohort could also be defined based on people's exposure or presence at a specific event. So there are cohorts around the World Trade Center, first responders and survivors of the atomic bomb blasts in Nagasaki and Hiroshima. There are also occupational cohorts. So we might sample a group of doctors or nurses, shipbuilders, educators, nuns, or metal workers, all of which have been done in previous studies. So the steps to developing a cohort study are to define your population. That's usually where we start in epidemiology, no matter what kind of activity we're doing. Then we want to also make sure we clearly define what our exposure is. Then we sample a group of people who are exposed and another group of people who are unexposed, follow them over time, and collect information on incident cases of disease. And then we compare the incidence between those two groups. So here's one example of a cohort study, and this one has been done in the past. The sample, the population, was postmenopausal women who met a variety of other characteristics, including the fact that they had not had cardiovascular disease or a heart attack previously. Then we divided them into, again, this is an observational study, so we're not assigning them to hormone replacement therapy or not. We're just looking at which women were hormone replacement therapy users and which ones were not. And then we followed both groups over time to see who developed an incident MI and those who didn't. Here's one more graphical example of what a cohort study looks like. So if this is our source population, we have a mixture of people who don't have the disease we're interested in, and then some people who do. So the green people represent those who don't have our outcome, and the red people do have the outcome we're looking at. So to do a cohort study, we'd select a sample from that population, and we'd exclude all the people who already have the disease. So in a cohort study, we start with people who are all free of the outcome that we're interested in, and then separate them into an exposed and unexposed group, and follow those two groups over time to identify incident cases of disease or the outcome we're looking for. Now, a cohort study always is following people over time. It is possible to do this retrospectively. So in a prospective cohort, that's where we'd start now, sample people, and follow them up into the future in real time to collect information on the outcome. But in a retrospective study, we might have a situation where we could use some kind of records, like medical records, to establish the cohort now, and then look back to determine what their exposure status was in the past. So this has the benefit of saving time, so we don't have to follow people for quite as long, but it does mean that we need to have really good data on historical exposure information so we can accurately identify our exposed and unexposed groups. So in general, cohort studies require long periods of follow-up, especially if we're doing them prospectively. So for that reason, they tend to be really good for short duration events between exposure and outcome, so things like pregnancy or a viral illness, sunburn, something that's relatively short term. They're also good for rare exposures because we're sampling an exposed group and an unexposed group. We can make sure that we have enough people in that exposed group to have the statistical power to detect an association with the outcome. So some advantages are that these can be really large studies. There could be thousands or tens of thousands of people involved in a cohort study. The duration can really vary depending on what you want to know, what you want to investigate. As we said before, they're useful for rare exposures. And there's what we call temporal sequence in place. So this just means that the exposure comes before the outcome. So ideally, that would always be the case in an analytic epidemiologic study. We want to make sure that the exposure is causing the outcome and not the other way around. So the way that we do that is in a cohort study, we start with people who didn't have the outcome, so we can be confident that the exposure came first. And we can also measure incidence, again, because we're starting with people who are all free of disease. We're measuring incidence over time. Limitations are that they can be costly because they are so long. But even in a shorter cohort, recruiting people and maintaining them, following them, collecting valid measures is a time-intensive activity. There can also be high rates of dropout over time, especially if it is a long study. and they're not good for evaluating rare outcomes. So even if we have a large group of people, if it's a really rare event, we may not have enough events in the cohort in our follow-up period to be able to detect associations. So case control studies, the other big class of analytic observational study that we use in epidemiology, start with people who have the disease and don't, and then identify past exposures. So here we're sampling based on outcome, while in a cohort study, we sampled based on exposure status. So in a case control, they're always retrospective. So we have to conduct interviews or, again, rely on some kind of records to evaluate people's past exposure. One of the other challenges with case control studies is identifying appropriate controls. So again, we want to make sure that people, that both our cases and controls are coming from the same source population. So basically, controls should be people who are from the same population, are at risk of developing the outcome, but don't currently have it. Often we'll see hospital-based case control studies where all the cases are people who have been hospitalized for a particular condition, and then controls are sampled from the same hospital but have a different condition. And that's not necessarily an appropriate control group, because really those underlying cases came from people in the community who both were and were not hospitalized. So ideally, you would probably want to seek controls who weren't hospitalized at all for any reason and include them in your study. But it can be very challenging to recruit controls in a case control study. First identifying them with an appropriate sampling frame, and then getting them to participate. So here's a similar graphic representation as the one we saw with cohort studies for case controls. So if we have that same source population, green people are those who don't have the disease of interest, the outcome, and red people do have the disease or the outcome of interest. In a case control study, we'd have our sample, and then we'd identify all those cases, the red people, and all the controls, the green people, and then ask them about their past exposures or use medical or some other kind of records to evaluate their past exposures. So these tend to be less time consuming than cohorts because they're always retrospective, but the interviews can be time intensive, and it may be costly to try to do exposure measurements. For example, there may be blood samples that are sitting in storage that hadn't been tested for the exposure you're interested in, so it's possible to do that, but there would be a cost associated with it. As I said before, it can be really difficult to find appropriate controls for your cases and then to get them to participate. Often people who have a disease are motivated and interested in finding out why they have that disease, but controls would not share the same motivation. And finally, for case control studies, you really need to make sure that you have some sound method for assessing past exposure. And what we worry about here is recall bias, in which those cases who have thought more about the causes of their disease or their past exposures might better remember their past exposures or might over-report them. So then you can end up with recall bias when you have a memory differential reporting between cases and controls. So the advantages of a case control are that they are good with rare outcomes because we're sampling based on outcome. They're typically not very time intensive, at least relatively speaking, relative to prospective cohorts. You might be able to use existing data to do the entire study. You can also match cases and controls to limit confounding. So for example, for every case, you might find one or two controls who are the same age and sex, and so then you know that age and sex wouldn't be confounding the association between the exposure and outcome that you're looking at. Case controls are also nice because you can look at multiple exposures. So in cases where we don't really know the cause of a disease, they're a nice option because we can find all the cases, find appropriate controls, and then ask about lots of different exposures in the past and try to see which one might be associated. The limitations of case controls are that we are kind of stuck with however many cases we can find and who agree to participate. So that can be a limiting factor. Again, we need a reliable source of past exposure information, and they're not good for rare exposures, just for rare outcomes. So when you are thinking about whether you should do a cohort or case control study, going back and thinking about these pros and cons of each, is a good step. If you're looking at a rare exposure and a short duration between exposure and outcome, then it might be a good option to use a cohort study. While if you're looking at something that's a rare outcome and happens over a relatively long period of time, and particularly if you're not sure exactly what exposure you're interested in, you want to look at multiple things, then a case control study might be a good option. So ideally in these analytic epidemiologic studies, we want to find causal factors. And causality goes beyond just association. So even if we've done a study and we've evaluated whether these exposures are associated with the outcome, and we'll talk about specific measures in just a minute, we want to think about whether that association is just a kind of numeric or statistical one, or if it's an actual causal one. So an association is just something that maybe has a strong correlation, or the covariance between two variables is high. But in causation, it's really a little bit more than just an association. So here's an example of something that has a pretty high association. This shows the blue line is US crude oil field production in the lower 48 over time. And then the red bars represent the number of songs that showed up in Rolling Stone's 500 greatest songs of all time by year. So you can see that there's actually a pretty close relationship between these two variables, that as just after those, we see the peak in the number of greatest songs, we also see a peak in crude oil production. So if you were looking at a correlation between these two, you would probably see a pretty strong one. However, you might reasonably say, what do these two have to do with each other? And the answer is probably nothing. So we wouldn't expect this to be a causal relationship. So this is just demonstrating that just because there's a strong association doesn't mean there's a causal relationship. So if we had a situation where everyone who was exposed developed the disease, for example, if all smokers developed lung cancer, or if everybody who was unexposed did not get the disease, in that case, no non-smokers develop lung cancer, then we would be pretty confident that the risk factor was associated with the disease. But these situations are very rare. We probably all know people who have smoked and who don't develop lung cancer. It's still a very rare outcome. And conversely, there are clearly people who have not smoked in their lifetime, but who do develop lung cancer. So in most situations, we need some other criteria to help us determine whether there's a causal association between exposure and outcome. So in the past, there was 5 kind of characteristics or conditions to consider when determining whether something was causal or not. This is the strength of association, so just how large is that effect estimate, how strong is the correlation or relationship between the two variables. What is the temporal sequence like? So as we said before, we want to make sure that exposure comes before the outcome. So is that the case? Consistency is the third factor to consider. Are multiple different people in different studies, in different settings, different populations finding similar results, finding the same association? Plausibility is next. This is basically considering whether there's some mechanism to explain the association. And this could be biologic, or it could just be, social, based on social conditions or social factors. And then finally, is there a dose response? So this isn't always possible to evaluate, but if there are graded levels of exposure, do those tend to be associated with higher risk of the outcome? So going back to the smoking and lung cancer example, if someone smoked for more years or had more lifetime pack years of exposure, do they have a higher risk of developing lung cancer? More recently, causal diagrams have been developed to evaluate whether an association is causal, and these are called directed acyclic graphs. So they're directed because all the arrows go in just one direction, which means and there's the acyclic part means there's no feedback loops. And it shows all causal relationships between variables. So this figure that we saw earlier is kind of a simple directed acyclic graph, and it can help us evaluate this causal relationship between having a caregiver and self-management by helping us identify those confounders so we can adjust for them in our analysis, and then also including mediators so that there are also ways to test for mediation and to understand which pathways are important. So when you see an association in an epidemiologic study, some things you should ask yourself are, could this association have been observed by chance? So this is where we look at things like p-values from statistical tests. Could the association be due to bias? And this is those systematic errors in how we conducted the study or how we analyzed the data. So some of the big ones are confounding bias, selection bias, information bias, including recall bias. And then does the association represent a cause and effect relationship? And so that's when you'd want to think through those additional criteria, use a directed acyclic graph or a DAG, and try to evaluate whether it's causal. So how do we measure those associations? How do we quantify the relationship between exposure and outcome? It really is based on risk, which, as we talked about before, is just chance or probability. So here we're typically talking about the probability that a disease will develop over a defined period of time. And again, we want to focus on population at risk, so people who have a non-zero chance of developing that disease. And so we typically calculate a risk ratio. And so this is the relative impact the risk factor has on developing disease in people who have been exposed and people who have not been exposed to our risk factor. So it's really just comparing the incidence in the exposed group to the incidence in the unexposed group. And so this gives us a measure of the strength of association. A relative risk of 1 or a risk ratio of 1 means that there's exactly the same risk in both groups. The incidence is the same in the exposed group and the unexposed group. So the farther you get away from 1, the stronger the association is. In cohort studies, risk ratios are called relative risks, and in case control studies, they're called odds ratios. And these two are slightly different. In both cases, we start with a contingency table or a 2x2 table where we have exposed and unexposed people in the rows and disease groups present and absent in the columns. And this is commonly how we label them A, B, C, D. So, for example, if we did a study where we wanted to know if participation in an intramural sports team made it more likely that someone visited the ER during the semester, we might sample 100 students who were on teams, so that would be our exposed group, 100 students who were not on an intramural team or unexposed group, follow them over the semester, and look at how many of them visited the ER. So we'll say 6 of those 100 people on teams went to the ER and 8 of people not on team went to the ER. So our exposure, again, is participation in an intramural sports team, and the outcome is visiting an ER during the semester. So we would set up our 2x2 table like this. Again, we had 6 of the team members and 8 of the non-team members visit the ER, and there were 100 people in both groups. So if we calculated a relative risk here, it's again just the incidence rate among the exposed group divided by the incidence rate in the unexposed group. So filling in the numbers, we'll go back to that slide in a minute. We would have 6 out of 100 in the exposed group divided by 8 out of 100 in the unexposed group. So our relative risk is 0.75. And that means it's less than 1. So it means that our exposed group has a lower risk of the outcome, in this case ER visits, than the unexposed group. And we'd say that the members of an intramural sports team have 0.75 times the risk of visiting the ER during the semester compared to people who weren't on an intramural sports team. So just going back, again, a relative risk of 1 means identical risk in the unexposed and exposed groups. And a relative risk can range from 0 to infinity. So anything above 1 indicates higher risk in the exposed group, and a relative risk of less than 1 means lower risk in the exposed group. And here's the interpretation. So again, this is saying that intramural sports participation reduces the risk of an ER visit during the semester, which might seem counterintuitive, and this is where, if you get a result that's counterintuitive, thinking through those steps that we talked about before, could it be due to statistical chance? We don't have a p-value here, so maybe. Could it be due to bias? And I think that's probably likely in this situation. We're just looking at intramural sports participation. So we're not including people who are on official athletic teams, and they might have a higher risk of injury or ER visits during the semester. It's also possible that because we didn't restrict our reason for ER visits, there could be lots of reasons other than injury that someone goes to the ER. So maybe those people who don't participate in sports are more likely to visit the ER. Maybe they have existing health conditions, existing injuries, other behaviors that make it more likely that they visit the ER. So that would be something that we would want to investigate, explore, and account for if we were really interested in the true association between participating in an intramural sports team and visiting the ER. One side note about relative risks, you can also use the inverse if it's easier for you to interpret. So if we did the inverse of 0.75, we'd get 1.33. And so that interpretation would be that students who were not on an intramural team were 1.33 times as likely, or 33% more likely, than students on an intramural team to visit the ER. So in case control studies, you may remember that we said we actually can't calculate incidence because we're sampling people based on the outcome. So we're picking a specific number of people with the disease and people without the disease. So it's an artificial number of cases in the population. So it doesn't necessarily reflect the prevalence of disease or certainly the incidence. And it's retrospective. So no incidence calculation in case control studies, which means we can't use the relative risk to measure the association. So instead, we use this ratio of odds. And so it's a similar interpretation to the relative risk, but not exactly the same. We'd start with the same setup, but instead of using incidence, the odds ratio ends up reducing to the cross product here. So A times D divided by B times C. And so if we get an odds ratio of 0.5, for example, it means the odds of having the outcome among the exposed group are half the odds of having the outcome among the unexposed group. So not exactly the same as a relative risk, but similar, just substitute the word odds. And in cases when the disease is rare, when the outcome is rare, the odds do approximately reflect the risk. So you'll see a lot of times people interpret odds ratios like they're relative risks. And so this is sometimes appropriate, again, if the outcome is really rare. But in cases where it's more common, that actually the two measures actually diverge quite a bit. So it's better to just stick with interpreting the odds ratio as odds rather than risk. So here's an example of calculating an odds ratio. Here we would sample, we want to know if agricultural pesticide exposure causes COPD. So we'd sample cases and controls, so 500 people with COPD and 500 without, go back and evaluate their past pesticide exposure. And we calculate an odds ratio of 2.1. So the interpretation would be that people with pesticide exposure had 2 times or 2.1 times the odds of developing COPD compared to people who didn't have pesticide exposure in the past. So relative risk and odds ratio, both risk ratios, both relative measures of risk. So we're comparing the association for the exposed group to the unexposed group. It's relative to the disease level in the unexposed population. The attributable risk is an absolute measure of risk. So this is also called the risk difference, and we just subtract the incidence in the exposed group or subtract the incidence in the unexposed group from the incidence in the exposed group. So it still gives us a measure of association, but it's also telling us the number, the absolute increase in the number of new cases of a disease that develop because of exposure. The attributable risk also varies based on how frequent the disease is in a population. So it varies with the relative measure of risk, but also the frequency. So if you have a more common disease, that will influence the attributable risk, whereas it would not make a difference in terms of relative measures of risk. So looking back at this 2x2 table, to calculate the attributable risk, you would do A over A plus B, which is just the incidence in the exposed group, minus C over C plus D, so minus the incidence in the unexposed group. Here's an example from a cohort study. And we can only use attributable risk in cohort studies since it relies on calculating incidence. But if we had 10,000 smokers and 10,000 non-smokers, so 10,000 exposed and 10,000 unexposed people in our cohort study, and we followed them up over time and identified 1,500 cases of lung cancer in the smokers and 100 cases of lung cancer in the non-smokers, we would just subtract the two. So 1,500 out of 10,000 minus, there's a divided sign there. The relative risk would be the incidence in the exposed divided by the incidence in the unexposed. So the relative risk here is 15. So that means smokers have 15 times the risk, 15 times as likely to develop lung cancer as non-smokers. So that's our relative measure of association. And then if we wanted to calculate the attributable risk or the risk difference, that's on the bottom here. So incidence in the exposed minus incidence in the unexposed, and we come up with 14 cases of lung cancer per 10,000 population are attributable to smoking. So again, slightly both measures of association between the exposure and outcome, but different kind of takes on it. So the risk ratio, relative risk, is telling us the increased likelihood of developing the outcome given that you're exposed, whereas the attributable risk is telling us how many cases of disease in this population could be prevented if we eliminated the exposure of smoking. So how many are caused by smoking? So if you want to use attributable risk, it can be really useful in population health and healthcare settings because it answers the question, if we eliminated this exposure, by how much could we reduce the incidence of disease among exposed people? So this 1,400 cases of lung cancer is preventable among smokers. Using the attributable risk requires that we already think there's a causal relationship between the exposure and outcome. So typically we don't do these initially, it's after we've built that evidence that there is a causal relationship. And it communicates the absolute additional burden of disease in exposed individuals as well. So patients could make decisions about engaging in particular behaviors based on the attributable risk. So it helps people make decisions about whether or not they want to modify or eliminate this exposure. It can also guide policy decisions about starting programs that are designed to remove exposures or limit exposures. So often in the literature, we see relative measures of risk, but attributable risk or absolute measures of risk can be really helpful from a policy and management perspective too. So it's a nice additional thing to include in studies.